Kia ora tātou. Welcome to the Fire Emergency New Zealand's Risk Reduction Continued Professional Development Series. This module is on smoke forecasting, fire detection and fire weather. It's an update on recent Scion research activities. It is designed to build your foundation knowledge in this area. Today's presenter is Ilze Pretorius, Atmospheric Dispersion Modeller at Scion. Welcome, Ilze.
Good day, my name is Ilze Pretorius and I'm an atmospheric scientist at Scion. My research interests include fire weather and smoke forecasting. Today I'm going to give you an overview of recent research activities in the atmospheric science space that we've undertaken at Scion. I will cover three different topics today. Namely the New Zealand real-time smoke forecasting system, which is currently under development, the 2020 Bushfire data quest, which was a research sprint in which 2 members of the Scion fire team participated in, and lastly, a research study we undertook to study the weather that influenced the Port Hills fire near Christchurch in 2017. Let's start with the real-time smoke forecasting system for New Zealand. Why smoke forecasting? The benefits of smoke forecasting is to warn people of smoke impacts so they can change their behavior to reduce their exposure to smoke. Children, the elderly, and people with pre-existing health conditions are especially vulnerable to the health impacts of smoke. Behavioral changes that we would like to induce include staying indoors, closing windows and doors, school closures, and in the worst case, evacuations. The image on the left shows the massive smoke plume from the Australian bushfires in January of this year, reaching all the way past New Zealand as captured by a satellite from space. The image on the right shows the impacts of this plume on the Auckland air quality. We would like to predict these type of events. But before I go into more details about smoke forecasting, I think it is important to look at what exactly smoke is and why it is a health concern. Smoke consists of a number of particulate and gaseous contaminants. These include fine particles, carbon monoxide, nitrogen oxides, polycyclic aromatic hydrocarbons, and volatile organic compounds. Population health exposure studies are mostly concerned with fine particulates as it poses the greatest health concern. But exposure to the full mixture of contaminants in smoke is likely to have additional health impacts that are currently very poorly understood. Why are we concerned about fine particulate matter? Particulate matter is defined according to its aerodynamic diameter and is often referred to as PM10, meaning particulate matter with a diameter of 10 micron or less, and PM2.5 with an aerodynamic diameter of 2.5 micron or less. The size of these particles with reference to beach sand and the human hair can be seen in this illustration. The finer or smaller the particle, the more toxic it is, as it can penetrate deeper into the lung and get past the body's natural defenses. PM2.5 penetrates all the way into the lung's alveoli, where it can get taken up by the bloodstream. It causes health impacts including respiratory illnesses, heart conditions, stroke, and some types of cancers. Particulate matter also blocks out light and therefore reduces visibility on roads, in the sky for aircraft, and it also impacts on tourism. The New Zealand Blue Sky Smoke Modelling Framework consists of a chain of independent models that are interlinked. Each of these links in the process answers a specific question to eventually lead to smoke dispersion. These links are as follows. The first link consists of fire information. Fire information is currently obtained from satellite detects. And from this, we can estimate the area of the fire, the point of ignition, and the time the fire started. In the future, we would like to include other sources of information, but for now, the only source is satellite detects. The second component in this chain of models is fuels. What burned? After this, we move on to fuel consumption. How much fuel burned? This moves us to what time of day did this burn, how much smoke was released, at what height was the smoke transported, and eventually, where will the smoke go? The other input the system takes is weather prediction model data. The New Zealand Blue Sky Smoke Modelling Framework is currently in its beta version, meaning that it's still being developed and tweaked for the New Zealand conditions. We are currently replacing some of the steps in the Blue Sky framework, these steps, with the Prometheus fire growth model, which is an international first, and this is to increase the accuracy of the smoke modeling and to provide real-time forecasts of fire spread. This system is currently running twice per day operationally, and it has already been used in a number of New Zealand fires, such as the Port Eels fire near Christchurch in 2017 and the Pigeon Valley fire near Nelson in 2019. I'll show you some results of this a bit later. The first input that this system takes is fire information, and as I've mentioned, information on the fire location and size is currently obtained from satellite detections. This image shows the actual fire perimeter of the Port Eels fire at the top right, which is compared to the hotspot that detects by the satellite in the top left. In the bottom, the fire area as calculated from the satellite detects for input into the smoke forecasting system is shown. This video shows the smoke forecasts that were done during the Pigeon Valley fires during February 2019. During this fire, let me start the video. There we go. During this fire, a number of communities were evacuated in order to reduce their smoke exposure. This video shows the predicted smoke dispersion from the Australian bushfires over New Zealand on the 2nd of February 2020. As I mentioned before, the New Zealand real-time smoke forecasting system is still being tweaked and improved. Recently, we upgraded the system to make use of state-of-the-art high-resolution numerical weather prediction modeling data. This image shows the output from the improved system. A further improvement is to replace some steps of the current smoke forecasting tool with the Prometheus fire spread model. This work is currently underway. This will increase the accuracy of the smoke model as it simulates real fire spread over the landscape, taking account of real fuels and terrain. It will also provide a first guess of where the fire will spread and this fire spread model can further be manually calibrated to what-if scenarios, which can be run later as more information on the fire is available. For those of you who don't know the Prometheus fire spread model, Prometheus simulates the spread of fire across a landscape with changing fuels and topography based on daily, hourly, or sub-hourly weather data. The Prometheus model is based on the Fire Weather Index and Fire Behavior Prediction subsystems of the Canadian Fire Danger Rating System and is adapted for New Zealand conditions. The output of the New Zealand real-time smoke forecasting system will be published on our website from December 2020 onwards. This will be open to the public. The fire spread modeling will also be provided to our stakeholders via the website, and these stakeholders include FENZ. So watch this space and keep an eye out on our website. While we are on the topic of our website, have you seen the Scion Rural Fire Research blog? You can register to receive email updates at the above address, and this way you can keep up to date with all the research activities undertaken by the Scion Fire team. Can artificial intelligence, primed with data from multiple satellites and local sensor networks, detect bushfires earlier, predict fire behavior, and help emergency services respond more effectively to protect homes, people, and valuable natural capital? This was the question posed by the 2020 Bushfire Data Quest, a one-week research sprint that combined researchers from diverse backgrounds with mentors and resources to tackle a specific real-world problem. Two members of the Scion Fire team, myself and Kate Malnick, our data scientist, were selected to compete in this challenge. We were teamed up with Jack White and Alex Codorono, an artificial intelligence expert and astrophysicist from Swinburne University in Australia. Our team worked on the problem of early fire detection from satellites. Our team concluded that an ideal fire detection system will detect fires very soon after ignition and provide accurate coordinates of the fire, enabling fast operational response and increasing the accuracy of fire spread models. It will do all this without increasing the number of false alarms, as those also cost time and money. With these goals in mind, we explored available satellite data. Polar orbiting satellites, such as MODIS, pass over the same region on Earth about twice a day. For early fire detection, this is not frequent enough, so we chose a geostationary satellite, Himawari 8, since it is always positioned over the Eastern Hemisphere and can provide images at every 10 minutes for the full disk and every 30 seconds to 2.5 minutes for selected regions. This high temporal resolution is absolutely necessary for early fire detection, but it comes at the cost of lower spatial resolution, which is 1 to 2 kilometers due to the satellite's high orbit. As a proof of concept, for this project, we chose to focus on the Auroral Valley Fire in southeastern Australia, which started in a remote part of a national park in January 2020. This is a 60 by 60 kilometer image from a polar orbiting satellite marked with the perimeter of the fire shortly after it was first detected. From the high altitude orbit of Himawari 8, with its 2 kilometer resolution, the infrared imagery of the area will look something like this. So the Auroral Valley Fire, which was 5 by 3 kilometers in size when it was first detected, was only 2.5 pixels in area and spanned 6 pixels as shown here. This poses a significant challenge for early detection. And in addition to this, there's also the issues of landscape heterogeneity, which makes it harder to detect the fire because of high noise. For example, the fire here is in the center of this image, but there's also an area here which is almost as bright. Current fire detection algorithms register a fire if a pixel reaches some predetermined brightness. This threshold is set high to exclude false alarms, such as hot rocks, for example. But that also means that it will miss fires when they are small in the early stages of development, therefore wasting precious time. To detect fires earlier, we made use of image enhancing techniques borrowed from astronomy. One such technique is image subtraction, at work here on the image in the image on the left. The small white square is blown up in the stamps below it. The first step stamp on the left is an image before a supernova event, while the stamp next to it, in the center, is an image taken after the supernova event. As you can see, or rather not see by eye, there is not much difference between the two. However, in the subtracted stamp, on the right-hand side, the supernova signal is clear as the only source. Next, on the right, image stacking allows us to improve the relative quality of an image. The technique does exactly what its name suggests. You stack images on top of one another, and because the errors in the pixels associated with the sensor on the telescope is randomly distributed, you get an improvement in the stacked images because the random error pixels rarely overlap. You can see an example of this in the two blown out stamps. The stamp on the right is much less fuzzy than the stamp on the left. We combined these approaches with an artificial intelligence method for enhancing an image, thereby improving the spatial resolution of the image. We could reduce the resolution of the Himawari satellite image from 2 by 2 kilometer pixels to 500 by 500 meter pixels by using this technique. So here is our detection algorithm at work. As a reminder, given the limited time of the research sprint, we focused our efforts on a single event as a proof of concept, the Auroral Valley Fire. There are 4 components to our detection method: the pre-processed stack, the incoming single image, the subtraction image, and a detection alert. The pre-processed stack combines 1 hour of images from a previous non-fire day. Next, we have the incoming image, which is subtracted from the pre-processed stack and produces the subtraction output. Of particular interest in the incoming image is that there were many pixels that appear to have similar intensities as the fire at the center, but these are gone in the subtraction image. So here we can see these high intensity pixels and also in the stack before the fire, but because they occur in the same place in the landscape and they occur every day, they are gone in the subtraction, which leaves us only with the signal from the fire. Currently, we determine how different a pixel is from its neighboring pixels statistically to decide if a fire detection has occurred. The takeaway here is that we can go from an incoming image to a fire alert within seconds.
Next, I want to give you a brief overview of our research about the weather influences on the Port Yields wildfire that occurred during February 2017 near Christchurch. This work was published in the Journal for Applied Meteorology and Climatology in February this year. And if anyone is interested to know more about this research, you are welcome to contact me. I will provide my email address in the last slide and I can send you this paper. The reason we were interested in this fire is because it made 2 rapid downhill runs on the 3rd and most active day of fire activity. As you are all probably well aware, rapid downhill runs are of special concern for firefighter safety, as it is generally assumed that fire spreads slower downhill than uphill. It is therefore important to try to understand rapid downhill spread events in order to learn from them to be able to predict them in the future. Both rapid downhill events occurred on 15 February. The first event, which I will refer to from now on as Event X, occurred very early in the morning between 3 a.m. and 6 a.m. when the fire made a downhill run towards Governor's Bay. Evacuations had to take place, and this fire spread was unexpected and therefore very dangerous. The fire spread in this direction towards Governor's Bay, but also in this direction and over here. The second rapid downhill spread event, denoted as Event Y, occurred later on the same day, roughly between 10:30 in the morning and 5 p.m. What was interesting about this event was that the downhill component of the spread, so the downhill component is in this direction down the hill, was lateral, which means that it was roughly perpendicular to the governing wind direction. So on a flat map, you can see that the governing wind direction is indicated by this blue arrow, but the downhill fire spread occurred along these in the direction of these purple arrows, which is lateral or perpendicular on the governing wind direction. To better understand the first rapid downhill spread event, Event X, we studied the Froude number. The Froude number is a dimensionless number that can be thought of as the ratio of the air's momentum to its weight. This number can be explained by using a skateboard and ramp analogy. When a skateboarder approaches a ramp with a lot of energy very fast and the skateboarder is relatively light, he will overshoot the back of the ramp, as what happens in this guy's case. This is equivalent to high wind speeds flowing over an obstacle in an unstable atmosphere and a high Froude number. When a skateboard has just enough energy, he will smoothly skate over the ramp without ever overshooting, and he will decelerate as he moves up the ramp and accelerate as he moves down the ramp as he converts his potential energy into kinetic energy. This is equivalent to air moving smoothly over a hill and a Froude number of exactly 1. When the skateboarder is very slow or he is very heavy, he will not make it up the ramp and he has no choice but to move around the ramp, as in the case of this guy. This is equivalent to low wind speeds blowing around an obstacle in a very stable atmosphere, at Froude numbers much smaller than 1. At Froude numbers near 1, some air or wind will move smoothly over the hill without separating in the lee of the hill, as in the case of this skateboard man, whereas some of the flow will move around the hill, as in the case of this guy. We think that this is exactly what happened during the downhill run by the Port Hills fire, and that air flowing smoothly over the hill pushed the fire downhill towards Governor's Bay as it is accelerated downward. This image of smoke and cloud hugging the terrain, taken at 6 a.m. towards the end of this rapid downhill fire spread event by the New Zealand Met Service webcam, clearly shows the flow attachment to the terrain and how the wind is moving smoothly over the terrain without ever detaching or overshooting, as in the case of our fast skateboarder. We believe that the combination of a stable atmosphere and low wind speeds can lead to unexpectedly fast downhill runs because of the acceleration effect as the air moves downhill. Firefighters should be aware of this possible risk. Now let's look at the second rapid downhill spread event, the event we called Event Y. This event started roughly around 10:30 in the morning, and it ended at around 5:30 in the afternoon. During this time, right about at 10:30, 11-ish, the land surface started to heat up and a cool easterly sea breeze undercut the overlying warm westerly flow, leading to a temperature inversion between the layers. This airflow can be seen in the smoke plume that was captured at 3 p.m. taken by the New Zealand Met Service webcam, where the plume looks like it's making a U-turn as it rises. So here we can see, if we look closely, the smoke rises in this direction, but here in the upper air, it makes a U-turn and starts to move 180 degrees pretty much in the opposite direction. We can also see the development of a pyrocumulus cloud at the top of the fire plume. It can also be seen in this image that stable conditions prevailed a lot, as there was a lack of significant vertical development of this pyrocumulus cloud, meaning that it didn't develop into a pyrocumulonimbus cloud, that typical anvil-shaped cloud that we often see in photographs of big fire events overseas. Wind measurements from aircraft and supported by numerical weather prediction modeling also shows the vertical wind shear. So here we can see both at 12 noon and at 6 p.m. that the wind direction at the surface is both higher than higher up. So we can see there's a decrease in wind speed with altitude, but it's also in a different direction than the wind speeds at higher levels. It is clear that the conditions that prevailed were not the usual unstable conditions often cited to be associated with blow-up conditions, but the fire behavior was still extremely active during this period. So let's look at some of the conditions that prevailed at this time. So let me explain this image. The fire spread between 10:30 and 1 is shown in this case, in this sort of hatched area. And the fire spread between 1 and 17:30 is shown in this area. The slope of the Port Hills gullies is indicated in yellow, blue, or green, where yellow slopes indicate slopes with an angle greater than 20 degrees. Blue slopes, or blue colors, indicate slopes between 25 and 40 degrees, and green indicates very steep slopes greater than 40 degrees. The grey arrows indicate the prevailing winds that as simulated by an atmospheric model. An arrow this size is roughly 7 meters per second. So fire spread, as I've mentioned, during this event occurred roughly laterally on the prevailing wind speed, on the prevailing wind direction, as we can see indicated by these grey arrows. Sharples and et al., a paper that was published in 2012, witnessed similar fire spread during the January 2030 or 23 alpine fires in southeastern Australia, and he termed this type of fire spread fire channeling. Him and his co-authors developed a set of conditions sufficient but not necessary for fire channeling to occur. These conditions are as follows. The wind is roughly perpendicular to terrain, ridges, and gullies. And if we look at this image, this condition was met in our case, because we can see these grey arrows are roughly perpendicular to our slope colors, the colors indicated in yellow, blue, and green. The topographic slope is greater than 26 to 30 degrees. In our case, we have many slopes that are greater than 26 degrees, but we also have quite a bit of slopes greater than 20 degrees. So this condition is mostly met. The upwind edge of the flaming zone is constrained by a major break in the topographic slope, i.e. a ridgeline. In this case, our flaming zone is constrained by this line, which is right sort of at the edge of one of these gullies. So this condition is also met. The last condition is that average wind speeds are around 8 to 11 meters per second. And as we can see, with this arrow indicates speed of 7 meters per second, most of the arrows sort of in this area are slightly higher. So it means that this condition is also met. A number of different mechanisms have been proposed for fire channeling. Due to a lack of sufficient data, it's impossible to say for sure what the mechanism was in this case, but two possibilities are likely. The first is that channeling of airflow caused this lateral spread as the airflow was channeled in these transverse narrow valleys. The second potential mechanism is a more complex phenomena where interaction between fire whirls formed in the lee of the terrain by the background winds and the vertical circulation of the pyroconvective plume of the updraft of the fire generated at the flank of the fire front interact to basically create fire spread in such a lateral direction. What complicates this further is that during this event, the two individual fires of the Fort Hills fire merged, and there was a low-level wind maximum, which we discussed a bit earlier. And both these phenomena could also influence fire activity significantly. So we will never know exactly what was happening here, but we can say that the combination of effects that we've seen in this case can lead to a situation where firefighters must be aware that rapid downhill lateral spread is possible. The research I presented to you today was a result of many team efforts, and I would like to acknowledge the following colleagues and collaborators for their hard work and contribution to each of the 3 research activities I presented to you today. Thank you so much for the opportunity to address you, and please contact me if you're interested in any further information or resources about this work. I believe there will now be opportunities for questions, but if I don't have the opportunity to answer your question today, please don't hesitate to email me and I'll try to get back to you with an answer as soon as possible. Thank you.
Thank you very much, Ilze. That's a great presentation. Actually, we've got one question just come here. With the slide on lateral spread, does the modelling take into account any turbulence created by the heat from the fire? Is that a significant factor?
Yes, yes, Jason, thanks. That's an excellent question. So the second mechanism that I spoke about, so the one possible mechanism we discussed was that it could have been fire channeling, which was, we saw that the atmosphere was conditionally stable, meaning that it was stable in the absence of the fire, but the fire itself actually caused instability. And so the fact that the atmosphere was sort of stable may have caused that lateral downhill flow. So that was the one mechanism. But the other mechanism I believe it was called, now I forgot the name of that mechanism, the second one I mentioned. Let me just go to my notes. But the second mechanism is actually, so let me just go down to that. I believe I didn't even mention it. It's got a complicated name, but basically the second mechanism is exactly that. It's an interaction between the firewall that forms in the lee of that terrain gully, and that is basically turbulence. So that's a turbulent effect, and we did not model that mechanism in this work because we didn't have enough information, because there were obviously no observations or measurements taken. But Jason Sharples, the guy that I mentioned that did work on this, they've modeled a couple of situations like this, and they could understand the interaction better. But yes, definitely turbulence generated from the heat of the fire, but then also the interaction between that heat plume and the terrain and the eddies that form in the lee of the terrain. It's basically a combination of those effects that cause that downhill run. So yes, that's absolutely true, that turbulence is incredibly important. If that was the mechanism in this case, so at this stage we are not sure which one of the two was the culprit, but there's a strong chance that this was the case, and in this case, yes, the turbulence was important.
Well, thank you, Ilze, for that explanation, and hope that answered your question, Jason. Thank you very much, Ilze, for the presentation. I really appreciate it.
Thank you so much. Bye-bye.